My name is Professor Duke Orata. We are moving on with our thermodynamics lectures. This is the third lecture. And so we are going to focus today on the first law of thermodynamics. First law of thermodynamics. And this is a very important law in thermodynamics. Let's call it first law. Now, think about it that you are heating a system and you are using different kinds of elements to heat that particular system. Suppose you're heating water in some container and you decide to use a heating filament or use a rotating paddle, or you can also decide to heat it by boiling up on some cooking stove. And so we think of this system where you have this water. We can talk of its initial state. Let's say it has an initial state. And this initial state is defined by some pressure, some volume, and some temperature. Let's call them P1, V1, and T1, where P is pressure 1, T is temperature 1, and V1 is volume 1. So let's call that the initial state of the system, because it has to be defined by these particular state functions, which you call pressure, volume, and temperature. And I'm going to talk about state function later on through in the other lectures, so probably at the end of this lecture. And then we heat that particular system. We have said we can use a heating filament. Use a heating filament. We can use a rotating paddle or a cooking stove, for example. And we change the state of this system to a final state. Let us say that this final state of the system is characterized by the variables, let's say P2, and T2. Now, if you calculate the work which is done in this particular process of changing the state of this particular system, if that process is carried out under adiabatic conditions, think of this as carried out under adiabatic conditions, where your system is represented by whatever process you're carrying out, and you have your surroundings here, like we have already mentioned in lecture 1, and we are saying it's an adiabatic condition. Under adiabatic conditions, that means no heat can be transferred between the system and the surroundings. There is no heat Q transferred between the system and the surroundings. So as you're carrying out this process of changing the state of your system from some initial state to some final state, using any of the methods which you have mentioned there, or other methods which can heat your system, but you are not allowing heat to be transferred to the surroundings, or to come from the surroundings to be transferred from the surroundings into the system. That means there's no thermal contact, like we had mentioned earlier on. Then you will find that the work done in changing the state of the system from the initial state to the final state, that work is the same irrespective of the method which you employed. So let us designate work as W, as you have already in the other lectures. The work done by using the heating filament, we are saying, will be equal to the work done using a cooking stove, and will be the same as the work done using the rotating paddle. So that means that this system is not interested in the method which you have used. It's only interested in what is the initial state and the final state of the system. So whatever method we have employed, whether you use the heating filament, cooking stove, a rotating paddle, the work done will be the same in those cases. So let's denote that work done under adiabatic conditions as W adiabatic. Let's call it W adiabatic. W adiabatic. Let's have W and adiabatic as a subscript. Now, suppose now you decide to repeat the same process, but allowing heat to be exchanged between the system and the surroundings. That is under non-adiabatic conditions. Let us now say this work is done under non-adiabatic conditions. In other words, heat can be transferred between the system and the surroundings. We still have our surroundings. And heat can be transferred between the system and the surroundings. So that Q is not zero now. Heat can be transferred between the system and the surroundings. So that's non-adiabatic conditions. So if you calculate the work done, under the non-adiabatic conditions, then you will find that in that particular case, the work done under adiabatic conditions and non-adiabatic conditions are not the same. So if we denote the works in terms of the processes, so we can say that work done under adiabatic conditions is not equal to the work done under non-adiabatic conditions. Now, a good illustration of work done under adiabatic conditions where the system is blind to the method which you have employed is, think of yourself as you are climbing a mountain, and the officials there will report if you are an individual or you are a group and you're climbing a mountain. They will simply say if the height of that mountain is, let us say, x1 meters. It says x1 meters. The height of the mountain is x1 meters. Then you started at this particular point with your mark there, and you reach the peak of the mountain. And there could be a case where you didn't know your way, so you started at this particular point. Let's call that A. This one, let's call B. You started at point A, and you went around this mountain. And you reached the peak. Yeah? Or you started at point C. And again, you follow that path, but you reach the peak of the mountain. This official will simply report that you have covered x1 meters. But you clearly see that when you followed path A, when from point A, you went round the mountain, and the distance definitely is far longer than x1. Then when you move directly from point B to the peak, and the same applies to point C, you have covered a longer distance. But the person reports that you have covered x1 meters. In other words, it doesn't matter the path you have followed. It doesn't matter what path you followed. He simply reports the difference between the peak and the base of the mountain, not taking into account whatever path you followed. So that's how you should think in terms of work done under adiabatic conditions. It doesn't care what kind of method you have employed, whether you use heating filament, whether you use the cooking stove, whether you use the rotating paddle, the work done will be the same. And that is just like when you have climbed the mountain in the example which you have given. Now, we have said that when work is done under non-adiabatic conditions and work done under adiabatic conditions, the two quantities are not the same. So the question is, what is this difference? That's the difference between work done under adiabatic conditions and the work done under non-adiabatic conditions. Adiabatic conditions is simply the heat absorbed in the system. And so the difference between adiabatic work and non-adiabatic work gives you the heat absorbed into the system or transferred into the system, and that gives you the mechanical definition of heat. This is the mechanical definition of heat. That's the mechanical definition of heat. Definition of heat. Now, what does this mean? This quantity W adiabatic, we said, depends on the state of the system, some initial value and some final value. So this quantity W adiabatic is related to the property of the state of the system, which we refer to as the internal energy of the system, denoted as U. Remember, we saw the U in lecture 2 when we talked of the isochoric heat capacity. We said CV was del U, del T with volume constant. That U, the internal energy, is what W adiabatic is. That W adiabatic represents that difference in this quantity, which is a property of the state of the system, U. So W adiabatic can therefore be expressed as delta U. And what is delta? Delta is that triangle you are seeing there, delta. And that delta is simply, it's a measurable difference. It's not infinitesimal differences which we mentioned in lecture 1. Those are very tiny differences. Delta is a measurable quantity. For example, if we talk of delta T, that is something you can do in the lab. You start boiling your water, the temperature was 10 degrees centigrade or 20 degrees centigrade to 70 degrees centigrade. The change in the temperature, delta T there, is 70 minus 20. It's measurable. So delta is a measurable quantity. It's not like the infinitesimal quantity which we use D, measurable quantity. So we are saying that W adiabatic is related to the property of the state of the system, which we call U of the internal energy, and that is given as delta U. That's given as delta U, or the U final quantity, the U of the final state minus the U of the initial state. That is delta U further can be written as U final minus U initial. Delta U can be written as U final minus U initial. And the infinitesimal expressions, in terms of infinitesimal quantities, we can write that as du. du. So that we are dealing with small quantities here, which is not just UF and UI, so we can have it in the infinitesimal notation, as we're going to see as we develop this first law. So we have said that W adiabatic minus W non-adiabatic gives you the heat absorbed in the system, which is Q. Therefore, now if we replace the W adiabatic with delta U, then we get that delta U minus W non-adiabatic is equals to Q. We can now remove the subscript non-adiabatic because now we are comfortable with delta U having taken over the expression for W adiabatic. So if we forget about that subscript there, then you can say delta U is equals to delta U minus W is equals to Q. Or we can rearrange this quantity and just say delta U is equals to Q plus W. This is the mathematical expression for first law of thermodynamics. That is delta U, first law of thermodynamics. Very important, you need to remember it always, that delta U is equals to Q plus W. Very important for us to note that. That means the change in the internal energy of the system is related to the amount of heat transferred within the system and the work done within the system. Now, very important to mention also that we can express this particular first law of thermodynamics in terms of infinitesimal quantities, which is very powerful for use in calculus, applying calculus to thermodynamics. So in terms of infinitesimal notation, then du will be equal to dq plus dw. But remember, in lecture 1, when we were dealing with work, we mentioned that if you integrate du, then you will get the cumulative quantities of the sum of those quantities. Now, let us look at that, because it brings us to a very important concept. So if we say du is equal to dq plus dw, and integrate these quantities, we will get delta u. Delta u, which is simply, if we had started from some initial state, let's call the initial state I, to some final state, some initial state I to some final state, some initial state I to some final state, then du will be given as u into final state minus initial state to the final state, and that will be given as q plus w. Why are we not talking of q initial to final state or w initial to final state? The reason is very, very simple. U is referred to as a state function. U is a state function. And when something is a state function, it depends on the state of the system. That's what we gotten when we talked about W adiabatic as being dependent only on the initial and final states of the system. It didn't matter whether you heated the system with a filament, a rotating paddle, or a cooking stove. So U is a state function. It depends on the state of the system. Depends on the state of the system. So in terms of mathematical definition of what U is being a state functions in the mathematical sense are those functions which are exact. Therefore, we say U is an exact differential. So state functions are exact differentials. And this is very, very important for you when you're working with functions so that you know whether the function is a state function or not a state function. They must be exact differentials. And what's an exact differential? So if you have a function of x, f as a function of x and y, then an exact differential can be written as df is given as del f del x, y constant dx plus del f del y, x constant dy. And so if you call these coefficients m and n, then being an exact differential, it must obey the concept that del m by del x keeping y constant must be the same as del n del y keeping x constant. And that is one way in which you will always be able to prove that whatever function you're dealing with is a state function. So U is one of the state functions. We are going to see that enthalpy is a state function, Gibbs free energy is a state function, and Helmholtz function is a state function, and so forth. Now, to the question of why did we have U final minus U initial or delta U as being equal to Q plus W? We didn't talk of delta Q or delta W. The reason is because heat and work are called path functions. Very important to note that heat and work are path functions. Heat and work, W, that's work, and heat, Q, heat, are path functions. They depend on the path which you follow. For example, if you follow a adiabatic path, Q is 0. If you follow non-adiabatic path, Q is not equals to 0. So work and heat are path functions. In other words, they are not exact differentials. Summary what we have covered today is that W adiabatic, work done under adiabatic conditions, does not depend on the method employed. The work will be the same irrespective of whichever method you've employed. If it is done under non-adiabatic conditions, the quantities will vary. The differences between work done under adiabatic conditions and non-adiabatic conditions gives you the heat absorbed by the system. That is the mechanical definition of heat. And you have seen that from that relationship, if you put in place of W adiabatic, which is related to the internal energy of the system, or that state function, which is related to that property of that particular system, then you get the first law, which is delta U is equals to Q plus W. And you can express that in the infinitesimal notation, and we're going to see why it's very important to express them in terms of infinitesimal notation to allow us to apply calculus in some of these thermodynamic calculations. And so we are going to see the next lectures where we are going to work on work, irreversible work, and reversible work.